welcome to all of you in the next class of this course. So, first let us recall what we have done in the last lecture. In the last lecture we have seen linear multi-step methods, how to drive linear multi-step methods, and in fact if any linear multi-step is given to us, we can also see how we can prove that that linear multi-step method is consistent or not. We have also done other kind of analysis, means how to find out the order of the linear multi-step method in the last lecture. We have also seen that linear multi-step method is a generalization of a Taylor series methods. In what sense it is called generalization of a Taylor series method? Because linear multi-step method connects the value of yx with its derivative only, while in Taylor series methods we have higher order derivatives term more than first order is also there. So, in that sense linear multi-step method is a generalization of a Taylor series method, which we have already discussed in the last lecture. But particularly in the last lecture we have seen a special case of a linear multi-step method, a special case in the sense that we focused only on two-step methods, but now the question comes up how we can generalize this to the k-step method. That is what we are going to discuss in the today's lecture. So, k-step methods, the 1 and 2 step methods that have been discussed so far generalize quite naturally to k-step methods. That is what I am presenting now. The most general method takes the form of following way. So, this you can see here it is n, here it is n plus k. Similar things are here at n plus k. So, there are how many when there are two terms involved, means we go from y0 to y1, then we call it as a one step methods, means two terms one step method. So, there here are n k plus 1 terms k step methods, that is quite natural as well. And as we have already seen that in one step as well as in two steps we have been talking about implicit and explicit. So, here again if beta k will be 0, then it will be called explicit method, otherwise it is of implicit type. The method has first and second characteristics polynomial also in the same fashion which we have already done in case of a two step linear multi-step methods. So, this will be my first characteristics polynomial r to the power k plus alpha k minus 1 r to the power k minus 1 alpha naught, and this will be my second characteristics polynomial. So, this is first and this is second, and at the same time let me also introduce what will be the associated linear difference operator in this case. So, the associated linear difference operator just becomes the difference of the left hand side and right hand side this way. Okay. So, as we get the general implicit k step linear multi-step method has 2k plus 1 arbitrary coefficient. Of course, in the right hand side how many coefficients are there? K plus 1. In the left hand side there are k coefficients. So, total number of a coefficients are 2k plus 1 in case of a implicit, and in case of a explicit 1 beta k is 0. So, of course, it will be 2k, that is what we can observe very easily. Now, let me talk about convergence and zero stability. Convergence of a linear multi-step method we have already seen earlier in case of a Euler method, as well as we have proved one theorem that convergent LMM is always consistent. Zero stability is the concept which we will be new for today's lecture. So, in order to solve the following initial value problem IVP for some interval, we choose a step size h, okay, and k step linear multi-step method will take the following form, okay, with the following starting values. So, why we are defining these many starting values? So, here is the point which you can observe very carefully, what is the disadvantage of 2-step, 3-step or multi-step method, because they are not self-starting, they are not self-starting. Initial condition is given to us at y naught, which is basically eta. So, to come from y naught to y1, we have to use some one-step methods, otherwise there is no way out. Okay, so, if we are starting with 2-step method, so we should know y naught and y1, only then we can determine y2. Okay. And that was also the drawback of one scheme which we saw in case of a Adam-Bashforth method, which was 2-step methods. So, that is not the self-starting method. At that point of time, I said I will discuss later what is the disadvantage of multi-step methods. So, means in nutshell you can say that linear multi-step method more than one step is not self-starting, means they are not self-starting. So, for from initial time to come to y1, you have to use another single step method. So, now let me see the definition of a convergence of a k-step method. So, the linear multi-step method with the starting values 4 satisfying this means all the approximations which you would have made at this of course, this is exact because you do not make any approximation to the initial conditions, said to be convergent provided all the approximation converge to the initial conditions, that is what we have seen. If for all IVP 3 convergent, if for all that poses a unique solution for all x. Okay. So, this condition is same which we have seen earlier also when we were looking at the definition of a convergence of a single step method. The only additional condition is here that all the initial approximation which you are making, that should also converge at j tends to 0, here as j. So, eta 0, eta 1, eta 2 all should converge. So, now let us discuss one another example where we can prove that this linear multi-step method is not convergent. How we can prove? So, that is what we are going to see here. The example is in front of us. If you recall your previous lecture, you can observe that in previous lecture for the same example we have proved that this method is consistent. We have proved in the previous lecture that it is an example of a consistent difference scheme, consistent difference scheme. So, what I am going to say here, if it is a consistent difference scheme, but still I will prove that it is not the convergent scheme. So, in the last lecture we have proved that the convergent method is consistent. Consistency is a necessary condition for convergence, but converse is not true. That is what we are going to show you with the help of following example. This scheme is consistent, which we have already proved in the last lecture, and we will see what else which is not true, because of that it is not convergent. So, we are applying this method to the following IVP with initial condition this. We are using the following starting values. So, of course, one assumption you could make that eta 1, which is 1 plus h, is also tending to 1 as h tending to 0. So, the initial assumption which we made it here is true. Okay. That is the first point to check. After that you will start checking other things. The method becomes, in this case is this. Why? Because f right hand side for this initial value problem is 0. So, that is why it will become yn plus 2 plus 4 yn minus 5n is equal to 0, because fn plus 1 is also 0, fn is also 0. The above equation is a two step constant coefficient difference equation whose auxiliary equation is this. What do you mean by this? I am going to explain you. So, this is basically a constant coefficient difference equation. Like so far you must have seen constant coefficient differential equation. When you call it as a constant coefficient differential equation, when the coefficient are constant. In the similar way, when the coefficient of this term and this coefficient of this term is 1, it is a constant, this is called constant coefficient difference equation. Okay. And how to can you recall how you solve differential equation? We solve a differential equation because we substitute, initially I am concentrating only on homogeneous because this is an example of a homogeneous difference equation. So, similar way I will also ask you to recall how you solve a homogeneous differential equation. You substitute y is equal to e to the power lambda x in such a way that it is a non-trivial solution of course, and then you try to find out lambda. So, here why you substitute e to the power lambda x there? Because the derivative of exponential is again in the form of exponential. So, in case of a difference equation, what we do? We substitute the solution yn is equal to Rn. Okay? That is what we are going to do. So, which is a non-trivial solution. So, here our aim is to find out n. Earlier in case of a differential equation, our aim was to find out this lambda. So, we substitute this value here. So, this will become Rn plus 2 plus 4 Rn plus 1 minus 5 Rn is equal to 0. Let me take out Rn common, then this will become this. Rn is 0, otherwise we will end up with a trivial solution, that is what I have already said. Then let us factorize this polynomial. So, which will be this. So, the general solution of a difference equation will be this. So, because r is 1, so if I substitute here, so one solution is 1 to the power n, which is 1, another solution is minus 5 to the power n. So, and then we take a linear combination of these two linearly independent solution. The same thing which we do when we try to find out the solution of a homogeneous differential equations. Okay. So, the concept remains same. So, finally, the general solution, I can call it also as a general solution because it is a homogeneous difference equation. Otherwise, I would have added this is a solution of a homogeneous equation plus particular solution, like the same way we were doing for in differential equations. Okay. So, this is a general solution of the difference equation where a and b are arbitrary constants. So, now the question is how to find out these arbitrary constant. Of course, there are two initial values which were given to us, y naught is equal to 1 and y1 is equal to 1 plus h. Okay. So, this so using these initial values, this and this, you can see we can get the value of a as follows and b as follows. Okay. So, finally, the solution of difference equation will be this. So, now if I substitute x is equal to 1, so basically nh is equal to 1. In that case, this h if you take inside, so nh is 1. So, basically in that case h will become 1 by n. So, this will tends to infinitive as h tends to 0. So, what we have observed that solution of difference equation is tending to infinitive. So, you are not getting the convergence, hence the method is not convergent, because the exact method should be called convergent if this condition is satisfied, not the infinitive, that we already know. So, this example shows that the consistency is not the sufficient condition for convergence, because in the last lecture we have seen that this difference equation was consistent, but now we have seen that but it is not a convergent, because what, okay, because you can easily get the solution of exact solution of this initial value problem, and you can see that s tends to 0, the solution of this difference equation is not converging to the solution of differential equation. So, this is an example where you can see that consistency is not the sufficient condition for convergence. So, now we have to observe why it is not convergent. Okay. It is basically, if you observe very carefully, we are not getting convergence because 5 to the power n tends to infinitive as s tends to 0. Okay. And it is happening because 5 is a number which is greater than 1. Okay. So, that is why, keeping that thing in mind, what we are doing, the first characteristics polynomial of any consistent 2-step LMM will factorize of course as such r minus 1, r minus a, and in this case we have seen a is minus 5, okay, which is leading to the trouble. So, a method with this characteristics polynomial applied to the following initial value problem would give a general solution, that is what we have seen, which suggests that we should restrict ourselves to method for which mod a should be less than 1, less than equal to 1. So, that mod a does not tends to infinitive with n. This turns out to be not quite sufficient as the next example shows, but right now our suggestion is that mod a should be less than equal to 1. In that case we may get the convergence, but we will see in the next example there is something more. So, now let us see the next example, which is this. So, if I look at this example, this is an example of a 2-step method, because n, n plus 1, n plus 2, and this is the example of a 3-step method. This is the first time when we are looking at any form of a 3-step method. So, and of course, initial value problem remains the same on which I wanted to apply my numerical method. So, what are the, of course, this is 3-step method. So, I have to take 3 starting values, y naught is 1, y1 is 1 minus h, y2 is 1 minus 2h. So, of course, I choose this in the following way, that as s tends to 0, y1 should also tends to 1, that is what it is happening. Similar thing, y2 should also tends to y2 as s tends to 0, that is what the initial phase of the convergence results which we should try to prove. Of course, I have chosen in such a way, y1 is 1 minus h, y2 is 1 minus 2h. And again, because I am applying to this initial value problem, so the homogeneous difference equation will become the this. Okay. Again, how to find out a solution, that I have already made it clear in the last example. I will substitute yn is equal to rn, and then so this will be rn plus 3 plus rn plus 2 minus rn plus 1 minus rn is equal to 0. Let me take out rn common, then rn plus r square minus r minus 1 is equal to 0. So, this becomes, so what is the factorization of this polynomial? So, r square r plus 1 minus 1 r plus 1 is equal to 0, r plus 1 r square minus 1 is equal to 0. Okay. So, which is same as this. So, in case of yeah, so this is a first characteristics polynomial. So, general solution of this can be written in the following way. So, how? Because if do you remember in case of a differential equation, if we have a repeating roots, we say c plus x d and then e to the power lambda x. So, similar things we are saying a, because one root is, it has 3 roots, the root 1 which has a simplicity 1, algebraic multiplicity has a 1, and the root minus 1 whose algebraic multiplicity is 2. So, this term corresponds to 1 and this term corresponds to minus 1. So, here we are writing b plus cn into minus 1 to the power n. Of course, the difference equation itself is a established field. So, here I am just trying to tell you the how to find out a solution in terms of a very basic difference equations, okay, because the aim of this course is not that, but of course, when we solve a differential equations with the numerical method, we end up with a difference equation. So, we should have some knowledge of a difference equation as well. With the given starting values, the solution can be shown to be this. Of course, now the question comes up how to find out these coefficient a, b, c. These coefficient I can also find out with these condition y naught is 1, y1 is 1 minus h, y2 is 1 minus 2h, and using those initial conditions, finally, the solution of difference equation will look like this. So, again the solution of the solution of initial value problem is this, exact solution of initial value problem is this. Therefore, at x is equal to 1, we can observe that y1 minus yn is tending to 1, which you can see, because if you will subtract this to 1, you will get the, because other terms will get to 0 and does not tends to 0 as s tends to 0. Hence, the method is consistent but not convergent. So, the observation from the last example did not go well in the following example as well, because we tried to put the condition that mod a should be less than equal to 1, but this is the example where all the roots are 1, but still now you should observe that why this is happening, why it is not tending to 0 as s tending to 0. So, again it is happening because minus 1 has a algebraic multiplicity of 2, and because of that this term has come n, okay. This n term has come, and because of that we are not getting the convergence. So, that is the observation, and based on these two observation, which we are going to formalize in terms of a definition, that a polynomial is said to satisfy the root condition if all the roots lie within or on the unit circle, with those on boundary being simple. What do you mean by all the value of all the roots should be strictly less than 1, but if it is at the boundary, it means r is equal to 1, then it should be only simple root, means its multiplicity should be only 1, that is the meaning. In other words, all roots satisfy mod r should be less than equal to 1, and any root that satisfy these things are simple. Okay. Simple means whose algebraic multiplicity is 1, which does not repeat. So, why we are formalizing this definition of a root condition? Because it plays an important role later on formalizing the concept of zero stability, and zero stability is something which is required for a consistent difference scheme to say that it is a convergent difference scheme. So, linear multi-step method is said to be zero stable if first characteristics polynomial rho r satisfy the root condition. So, again we are formalizing the definition of zero stability with the help of first characteristics polynomial in the following way, that if first characteristics polynomial satisfy the root condition, it means that all the roots of a first characteristics polynomial should be less than equal to 1, and if there is any root whose value is 1, it should be only simple. So, with this notion of a zero stability, we can prove one theorem. Of course, in this course we are not looking at the proof of this theorem, which you can see in any advanced book on numerical methods for ordinary differential equations or in any advanced course. But as far as this course is concerned, we are not looking at the proof of the theorem, but the essence of the theorem should be clear to you once the statement is clear. And linear multi-step method is convergent if it is both consistent and zero stability. So, that is what we were keep saying, that something more is required when you can say that consistent difference scheme is convergent, and what that thing more is? Zero stability. So, I hope consistency is clear to you, zero stability is clear to you. And you know, when we were dealing with Taylor series method, we have not paid any attention at all to zero stability. Why? Because if you look at the form of a Taylor series method, it is always in the following way: yn minus yn is equal to something. So, what is the first characteristics polynomial in this case is r minus 1. So, this it means root is this. So, it always satisfy the root condition. That is why we were not bothering at that point of time. So, now one another theorem which says that the order P of a stable k step linear multi-step method will satisfy the following inequality, means the order should be less than equal to k plus 2 if k is even. Order P should be less, where k is the k is step and order. So, it means this theorem also tells me that you cannot get any desired order. So, P will always be less than equal to k plus 1 if k is odd. Moreover, P will be less than equal to k if beta k is less than equal to 0, in particular for all explicit methods, because in case of explicit method beta k is 0, that is what we have already seen. So, this theorem is telling that there is a relationship between the order of the method and step of the method. It is not that once you say that with the k step method I can get the desired order. No, it is not the case, because this theorem limits that thing. Okay. Now, let me give you the more formal way of introducing this linear multi-step methods. The first category of the methods which we have already seen is Adam-Bashforth family, or some people call it as a formulas, methods, rules. So, it is up to you how you want to call it. The form of a Adam-Bashforth family will be in the following way. That is what we have already seen. Of course, here there is beta k is 0, that is why we are starting with beta k minus 1, because this comes under the category of a explicit methods. The first characteristics polynomial corresponds to Adam-Bashforth family will be this r to the power k, r to minus r to the power k minus 1. So, this has only one simple root, r is equal to 1. So, of course, if this is the case, zero stability is always satisfied in case of a Adam-Bashforth family. That is what we wanted to observe. So, if k is equal to 1, this is the case, and the associated linear difference operator will be this, and for consistency we get beta naught is equal to 1, hence we get forward Euler. So, basically we are constructing in such a way that it will be always consistent, and we are choosing the coefficient in such a way, sorry, let me again repeat my statement. We are making this template in such a way that first order characteristics polynomial will satisfy the root condition. It means zero stability is always satisfied, and we are choosing the coefficient in such a way that the scheme is consistent. Okay. So, it means we get forward Euler method, which we can from the construction itself we can say it is consistent and zero stable. So, if you have proved this two things, you can say it is convergent also. Though in the first lecture of this part of the course we have already proved separately also that how you can prove the convergence of Euler method without going into the consistency and zero stability concept. So, now you can prove in two ways, one is to prove directly, another is with the help of consistency and zero stability, and then with the help of the following theorem which you have seen here, that linear multi-step method is convergent if and only if it is both consistent and zero stable. Okay. So, now let me try for k is equal to 2, then our difference equation will be this, and if you remember from the previous lecture we have separately dealt this kind of a difference equations, and we proved found beta naught beta 1 in such a way that the method should be consistent, and the first characteristics polynomial of this difference equation is automatically satisfying the root conditions. That is what we have in fact said in a more general case. So, in a particular case of course, that condition will always be true. Now, if I say k is equal to 3, then the difference equation will be this, and we will find out these coefficient so that the resulting method is consistent. First characteristics polynomial is automatically satisfying the root conditions. So, we get following coefficients, okay. And finally, the difference equation of a 3-step Adam-Bashforth method will be this. So, this is the first time we are looking the exact form of a 3-step Adam-Bashforth method, which has a order p. Order also you can determine with the order of the consistency. This is also called AB3 method. That is what this is, just a abbreviation AB1, AB2, AB3. Now, let me come to the next family, which we call it as a Adams-Moulton family. These are the implicit version of Adam-Bashforth family having the following form. So, again we will work out for some special cases. If k is equal to 1, the difference equation will be this, and hence we will find out the coefficient in such a way that the resulting difference scheme becomes consistent, while the stability polynomial in this case will be again satisfying the root conditions, which you can observe from left hand side. So, if we get this, which is implicit Euler method. So, finally, we get this method which we call it as a AM1, okay, one step methods. The two step Adams-Moulton methods has order 3, not the maximum possible order k. How you are determining maximum possible order k? Because if it is a two step, you can see from the following theorem, if it is two step means k is even, and k is even 2 steps, so k is 2, so p should be less than equal to 4. So, the order of the method should be either 4 or less than, but so maximum is 4. So, but in this case we are getting it should be 3, has order 3, not the maximum possible order 4, and the difference equation is given by the following formula. So, again this is a two step Adams-Moulton method. For k is equal to 3, the difference equation will become. So, this you can take it, both the things you can take it as a exercise, and try to find out the coefficient, because I am directly giving you the difference equation how it will look like. So, both of them are exercise where you have to prove how these coefficients are 5 by 12, 8 by 12, minus 1 by 12. In this case 9 by 24, 19 by 24, minus 5 by 24 and 1 by 24. So, these two things you can take it as exercise to prove that what will be the 2-step Adams-Moulton method and what will be the 3-step Adams-Moulton method. In fact, if you want more exercise, you can also prove for k is equal to 4, 5, 6, it is up to you. Okay. But what is the disadvantage of if you keep adding the steps? There will be a problem, it will not be self-starting till that point. If it is a 3-step, so you have to initially choose 3 values, why not y1, y2. So, that is the problem, and that is the cost we are paying to not to compute higher order derivatives. Okay. So, of course, we have to pay some cost. And the next is Nystrom method. These are explicit methods with k is greater than equal to 2 having the following form. Okay. So, again as I have already mentioned, k should be greater than equal to 2. So, for k is equal to 2 we will have the following form. So, again if you look at the first characteristics polynomial will be this. So, the roots of this polynomial will be this. So, it automatically satisfies the root conditions, and coefficient will be determined in such a way that the scheme is consistent. So, finally, I end up with this, which is again a different method in this sense we have not seen so far, and it is called leapfrog or midpoint rule. This is an example of a 2-step method again, because n plus 1, n plus 2. It is explicit because the left hand side term involves n plus 2, while in the right hand side there is no terms which involves any value at n plus 2. And why it is called a midpoint? Because if you try to find out this difference scheme with the numerical quadrature, you will be able to justify. So, this is again you can take it as an exercise. You try to obtain this difference scheme with the help of numerical quadrature formulae. So, try to, let me write down here, try to get this difference scheme with the help of numerical quadrature. Because in the last lecture you can recall I have derived couple of schemes with the alternate wave that was numerical quadrature formulae, and that is how I also justified why trapezoidal method was called trapezoidal method. In a same way you can justify this also why it is called midpoint rule. So, that you can take it as a exercise. So, the next is Milne-Simpson's method. These are again implicit analogues of Nystrom methods, like initially we started with Adam-Bashforth, Adams-Moulton were the implicit version of Adam-Bashforth. Similar way we said Nystrom methods, and then these are the implicit versions of a Nystrom method. So, here the difference scheme will look like in the following form. So, again from the left hand side you can observe that first characteristics polynomial will be automatically satisfying the root condition, because there is no difference in the left hand side, because this is just the implicit analogous of the Nystrom method. So, the difference will lie in the right hand side. So, in fact, I do not need to say anything about the 0 stability, and then coefficient will be chosen in such a way that resulting difference scheme will become the consistent. So, finally, for k is equal to 2 we get the following values of coefficient after collecting the terms. Because in all these examples you can try to find out, you can take it as exercise and try to find out these coefficients. The same way in the last lecture I have done couple of examples. So, hence we get the following difference equations. Okay. So, there are, so to determine these coefficients you have to choose your order accordingly, which is nothing but the Simpson rules. So, here again let me say why it is called Simpson rule, that also you can justify once you start deriving the same formula with the help of numerical quadrature. So, again point which I am mentioning here, or you can say you can guess whether it is related to Simpson rule of numerical quadrature or not, that is what you can check. And the next is backward differentiation formulae. So, in backward differentiation formulae, the scheme will be in the following way. So, for k is equal to 1, we have this, okay, and hence associated linear difference operator we will write, so that we can determine the coefficients in such a way that the scheme is consistent. And what will be the form of first characteristics polynomial, that also you can observe in the following case. Okay. So, the root is 1 plus r plus alpha naught. So, alpha naught we are choosing from here also, alpha naught is 1. So, root is 1. So, means it satisfies the 0 stability as well, and the scheme will be this, for k is equal to this, you end up with this. So, basically in the backward differentiation formula we are using on the value of y dash at n plus k, we are not using the other values, that is the difference if you observe from here to the previous cases. Okay. And while in the left hand side we involve yn plus k, yn plus k minus 1 and yn. So, that is different template at all. So, basically we have seen 4 categories, and in all 4 categories we have seen the different templates. So, sometimes for the same order, suppose you wanted to work with the third order numerical method. So, you may end up with the different template. So, in that case you have to choose whether you want to use explicit method, implicit method. So far I have also shown you one disadvantage of implicit method when we were working with the set of a differential equations, and I also explain, or you can choose among single step method, two step method, though I have also shown you the disadvantage of multi step methods. So, means it is up to you how you choose which you want. Okay. So, with this I am stopping at this point of time, and in the next lecture I will try to show you some of the examples how it works numerically with the help of MATLAB software. Okay. Thank you very much for your attention.